All right, let me start. Hello, welcome. Welcome for this quite unusual session. If you don't like code, you are not going to be very happy here, because this session is almost 90% just code. So my name is Clément Escoffier. I'm working at Red Hat in the Vertex team, and I'm going to do in 35 minutes a couple of microservices. I'm going to develop them using a reactive platform, reactive toolkit, which is named Eclipse Vertex. So how does reactive fit in this world? So first, reactive means reacting to stimuli, whatever they are. Keystrokes, failures, events, user requests, all of them are stimuli, events, messages. So almost everything we built since the 60s is a little bit reactive because it's in the nature of software to react to the user input and operating system order and stuff like that. However, in the last few years, we had three main clusters that have emerged in the reactive landscape. First, your goal, reactive systems. Reactive systems are applications that follow a set of architectural constraints that let them be responsive in face of failures and even under load. To do that, there is one key word, asynchronous. All your components are going to use asynchronous message pacing. However, asynchronous, well, as a developer, we don't really like that. It's kind of complicated. Who loves callbacks? See? Oh, one. Whoa, are you a JavaScript developer? No, just to know. So, fortunately, we have reactive programming that lets you compose efficiently, elegantly, asynchronous and event-driven software. It's based on the idea that everything is a data stream. It's kind of weird. It's really a paradigm shift. So everything is a data stream, and in a data stream, it's totally asynchronous because you don't know when the data will be there. So you observe this data stream, and you will be notified when there is data, when there is failures, or when the stream completes. Failure is very important because when you do asynchrony and asynchronous development, forget about exceptions. You can't throw them. You are not in the same thread. So you can throw the exception, no one is going to listen. So you really need to think about error propagation early. There is another issue with a data stream. Imagine that you have a very fast producer and a very slow consumer. What is going to happen? Well, the fast producer is going to send data to the data stream. It's going to buffer on the customer side. What happens when the buffer is full? Out of memory, you're dead. It's kind of weird because that's exactly what we don't want. We want to stay responsive under load. So reactive streams is a back pressure protocol, a non-blocking and asynchronous back pressure protocol that lets the consumer tell to the provider when they are ready to handle some load. This looks simple. This is very complicated. Don't even try to develop such kind of things. Unfortunately, if you use a modern reactive programming library, it's all made for you. You don't have to do anything. I also mentioned that I'm going to develop microservices. I'm not going to develop one microservices because one microservices is not microservices. A microservice system starts at 2 microservices. So I'm going to develop 2. One is already deployed, so it will be 3 at the end. The nature of microservices is that everything is going to be distributed. Yeah, so we can summarize that everything is going to fail. At some point, it's going to fail. So basically, building microservices means you're prepared to fail and to handle those failures. That's why microservices and reactive systems fit together, because this one, reactive systems, are made to survive failures. So let's start some code now. I have prepared a very, very simple project. That's going to be my first microservice. It's called Shopping Backend because I forgot to mention that. I'm also going to fix the first world problem that we all have. How do you manage your shopping list? Right? First world problem. So we are going to do that with microservices. It's way cooler than having Post-it on a fridge. So this is a Maven project. it has the vertex BOM, okay, and actually the only thing that is required to create a vertex application is this dependency here, vertex core. I've added a few others that we are going to use as later in the presentation, and we have the Vertex Maven plugin. It's absolutely not mandatory. You can package your Vertex application as you want, even in a Spring Boot application, in Java EE application, in an Eclipse RCP application, you do whatever you want, but the Vertex Maven plugin has a very nice auto reload, and we are going to do that. So I have declared vertical. Vertical is a class. This is a class. This is my vertical, and it's just something that is deployed on top of Vertex. It has access to the instantiated Vertex object, so let's start with it. Vertex.create HTTP server. Let's do something cool. I'm registering a handler, again, reactive, so every time I will get a request, it's going to call this handler. That's how I react to my stimuli. And inside this handler, I'm going to do something like bonjour. For once, I can do it in French. Cool. And I'm going to start that on the port 8080. So now I go there. I'll just do vertex run. And it should do something. Yep, started. So it's compiling, and here we go. We should have something. Yeah, bonjour. So, okay. Now we want to manage our shopping list, and we want to develop a kind of HTTP/RESTful-ish interface. We won't debate about whether or not it's RESTful. It's not. It's just HTTP API. Okay, but if I start doing this here, that's going to be very complicated, right? If it's a get on /shopping, I do that. If it's a post and so, no, we are not going to do that. Fortunately, Vertex comes with a very handy component named Vertex Web that provides something called a router. On a router, you declare routes. For example, on /, I say, okay, let's say bonjour. Okay, now I go back here and just need to pass the router instead of this handler. I pass the accept method. So what is going on here is that the handler is this accept method that will receive the HTTP request, look at the set of routes, call the right handler. Let's develop a little bit my REST API. So on /shopping, I will call get list. On post on shopping, I will say add to list. On delete, because sometimes we don't need things, I will take the product name as parameter, and I will say remove from list. And that's more or less it. Oh no, there is one thing I tend to forget. Root.handler body handler. Great. By default, for performance reasons, Vertex won't parse your body. So you have to tell it, say, okay, you need to parse the body. I will need to implement all those methods, but first I need a way to handle my list. And let's do something amazingly confusing. Let's have a map that contains the strings of the product name and the number of items I need to buy, and let's call it list. I always wanted to call my a map a list. Yeah, naming. Okay, it's time to implement those methods. Let's start with a get list. So get list, well, microservices are distributed, but also a lot about JSON. So we are going to return JSON objects. So I'm going to take my response and say, yeah, let's encode your list as JSON. Oh, encode prettily. It's important. Then we are going to add to list. So I expect to receive a JSON object as body. Okay, this is my body here. A body has a name, as a product name, so it's name. And we will have an integer as quantity. Integer quantity. And if quantity is not there, let's say that the sensible default is 1. I'm going to add that to my list. Okay, and well, not even return, let's just get list. So we add, and then we will just run this. We just have to do remove from list now. So remove from list, in the root I have declared this name here, which is a pass parameter. So I will get the name of my product, I will remove it from my list, and just do get list. Okay. So now it should start saying that everything is fine. Yeah. So here we have bonjour, and here we have shopping, an empty shopping list. Let's start to add things in my shopping list. Shopping, name equals bacon, quantity equals 1. So this. Yoo-hoo, I have bacon. I need coffee. Lots of coffee. Yeah, 12 coffee. Okay, works. Let's try to delete something. Bacon. Bacon is not good for my diet. Okay, we have our HTTP/REST API that is working. But I want to deploy that on the cloud. So because I'm not 100% sure of the Wi-Fi here, I have run the cloud on my own laptop. But first, let's explain a couple of things. I'm going to use Kubernetes, and I'm going to use an enterprise-grade Kubernetes distribution, which we do at Red Hat. It's named OpenShift. It's completely open source. Basically, you have a container host, whatever it is. Obviously, we will recommend you RHEL, but I'm on a Mac and it works pretty well. You can use any operating system, even Windows that works. And then we have Kubernetes, unchanged Kubernetes, where that is going to handle all the orchestration between your different containers, because in Kubernetes world, everything is container. So it's going to manage the registry, where do you put your image, the storage, how do you mount volume, how do you unmount volume, log and metrics, because it seems to be important when something crashes, and security and all the boring stuff that we don't want to mention. On top of that, OpenShift add a couple of things. The two main features for me are the build and the deployment. Build. I'm not going to build the container myself. I will ask OpenShift to do it for me because I found that very boring. Docker build. Oh, what's the parameter again? I don't know. So I will just say, OpenShift, you have a Docker file, do it. And it does that. And deployment. Deployment is also interesting because we will tell him, yeah, keep 2 instances of this application. And it will always keep 2 instances. If one crash, it will restart it. But it goes further. If we can have rolling updates. So as soon as I'm going to update my Docker image, you say, hey, you are updating the Docker image. And it's going to update the new microservice. Start it. And when it started, we'll stop the first one and reroute traffic. We are going to see that. However, I mentioned containers a couple of times. And there is a big, big lie about containers. Containers are not about isolation. They are pretty bad at isolating things. Containers is about sharing. It's much better. Why are you using containers? To increase your deployment strategy. It means you can run more applications on the same node. That means that all your containers are going to use the same resources, the same CPU, same memory, and so on. That also means that if you have one container that is a little bit too eager in terms of resources, it's going to decrease the efficiency of the other one because the resources are taken by the first one. So all we do for that, we introduce quota. What happens when one of your microservices hits the quota? It's killed. That's how the containers works. So you don't really want that. So when you put something in a container, you need to be sure that it's going to efficiently use your resources, CPU and memory. For that, if you need to scale, don't use thread-based approach. Threads are too expensive in terms of memory, and they are going to eat your CPU quota. We did a test. We ran containers with 8,000 threads, which is not that much, actually. To handle 8,000 requests at the same time, we need this. 25% of CPU quota was just thread switching. thread switching is not about your business logic. It's just completely useless. So with Vertex, fortunately, you don't have that. You are going to use one single thread, and we can handle 10,000 requests with one single thread. Okay. No, I will do that first. The first time you go to the Kubernetes world, you will say, oh man, last time I checked clouds, that was all about XML. That was painful, but here it's all about YAML. So it's like XML, but we remove all the formats and stuff like that, and you are going to spend your time debugging missing or extra spaces. It's great. And it has a lot of concepts. You start, you say, okay, what is a deployment? What is a pod? So I draw this one, which explains a little bit how it works. We have source code. That's what we do as developer. We are going to say to OpenShift, okay, here is how you are going to build this. So basically, we give him a Docker file, and it's going to build a Docker image that goes in the Kubernetes registry. Then we have a deployment configuration that is a YAML document that we can ask him to do a generic one that will take a Docker image and instantiate a pod. A pod is a group of containers. Generally one, or generally. 6 months ago it was always one, and since 6 months with Istio and Service Mesh and sidecaring, now it's two. But here I'm going to use only one. So then you have your containers running inside your pod. On the other side you have users that will hit a root. A root is a public URL on which they can access your service. Your root is actually delegating to a service object, that is a Kubernetes object, that is going to delegate to a group of pods based on labels. In most of the case, you have one, so it's going to always deploy on the same one. So let's see how it works. So when we want to do a container, the first thing we will do is a Docker file. And this Docker file is going to be very simple. I need Java. I will expose 8080. Let's build a fat jar and put that somewhere else and start it with java-jar. And this is because Vertex has some, try to write in the current working directory, which is not a good practice, so I just tell him, don't do that. I will stop this. Build with Docker. So basically what it will do here, it will declare a build on OpenShift. It will build the fat jar using the Vertex Maven plugin, send this fat jar to OpenShift with the Docker file, and OpenShift say, oh, there is a Docker file. I know what to do with that. And it's going to execute this operation here. So let's check. We should have a build that is this one here. Let's have a look at the log from Java 8, work directory, and so on and so on. So it's exactly my Docker file that has been executed on OpenShift. I don't even have Docker on my system anymore. I have a very old version. And it has been deployed, so it also declares the deployment. And the deployment is, okay, create one service, one root, one pod. Easy. So now we have my pod here. Inside my pod, I have one container. Where is my container? Shopping backend. Okay. And I have my root. And if I do that, I should have access to Bonjour and to my shopping list. Okay, cool. So let's add some stuff in my shopping list. And now I have my perfect breakfast, eggs, bacon, and coffee. So great, but if you are running on the cloud, the first thing you will want to do is, well, I want to scale. And what you will do is that click on this button here and say, yeah, I need 2 instances. And it will just start a new instances, so another pod with the same containers, and everything is fine. Right? It's fine. Refresh? Yeah, it works. Works. Let me check one thing first. If I do a curl, hey, my shopping list is empty. Hello? This one is full, this one is empty. We just are seeing the split shopping list problem. One of my pods got the shopping list in its memory, the other one does not. So they need to share the same database. So we need to improve this and to not keep this list here, but use a database or a data store. I'm going to use Redis because Redis is cool. It's a kind of distributed key value store. I'm not really good at Redis, so I probably will do lots of mistakes or I structure my data. But for this, I need a Redis client. We call Redis. So, okay, I have a Redis client, but how do I find my Redis client? I'm on the cloud. For this, you are going to use service discovery. Okay. Here is I have my service discovery, and from my service discovery, I will ask to get a Redis data source, and I want to filter it, and let's say that I want the service that has the name Redis, and from where comes this name? If you see here, I've deployed Redis here, and the service name is here. The service name is used for internal communication. So everybody in my project, in my OpenShift project or Kubernetes project, can access it using this name here. I could have used DNS too. I prefer using service discovery. It's way more dynamic. So obviously, the lookup can fail. So when it fails, we'll do something very, very smart. We write an error message. Or if it's there, then I got my Redis, and I will just do this. Why? Can I do that? This is a field. I should do synchronize or something like that. I don't know on which thread I'm called here. That's the beauty of Vertex. As you have a single thread, you can't have concurrent access. You don't need to protect your state. So no synchronize and no volatile. Nobody understands volatile anyway, so that's fine. And then I'm going to start my HTTP server when this is done. Okay. So I need to modify this code here. So remove from list. Instead of doing this, I'm going to do redis.hashdel shopping. It's where I'm going to store my shopping key, and I want to remove the product name named. I don't care about the result, and I will just call getList when this is done. Okay. Then here we will do almost the same. Redis.hashset. Yeah. Shopping. Okay. The field is the name. The quantity is quantity.toString because our API imposes that it's a string. We need to fix that at some point. And let's call getList when it's done. So I say when it's done because the callback is only called when the operation has been completed or failed. And this one is a little bit more tricky. Redis.hashgetAll. I want the object stored as a shopping key. Then I have a result, and if it failed, then I will just see.fail, saying that something bad happened. Let's use 500, whatever. And if it did not fail, then that means I retrieve a JSON object from Redis, and I'm just going to write it inside my response. Result.encode prettily, and that's all. So in this vertical, I'm using callbacks just so that you can quickly understand how asynchronous programming works. When an operation is done, the callback is called, and so on. In the second microservice, I'm going to use reactive programming, so we can remove all those callbacks. So let's redeploy that. Hopefully, it's going to compile. And it does compile. Woohoo. And here we should see a rolling update. So it means that we have the build that is going to be executed here. So it's receiving, so it will run the Docker build. And here it's implementing a rolling update, meaning that it's going to start a new container and start the second one as soon as the first one is ready. as soon as the first one is ready? Yeah, because Kubernetes try to make a guess when your containers is ready. And believe me, it's not very good at guessing. We need to help it. We are doing that. So, but let's first check if it works. So it's empty. I will repopulate. No. Repopulate my shopping list. Here it is. And now if I go here, we have the shopping list. Okay, so now it works. We don't have the split shopping list issue anymore. Everybody is using the same version. Nice. So how do we improve this rolling update things? We go to deployment. Here we go to configuration, and it's mentioned that we need to add health checks. Kubernetes has two types of health checks, readiness and liveness. Readiness lets you tell Kubernetes when you are ready. Liveness lets you tell Kubernetes when you are dead, when you don't work anymore. I'm going to do something very bad. I'm going to use the same checks for both, but normally it should be two different checks because being ready and being alive are really two different things. Save. Okay. Okay, so it's redoing it with the update, and I believe. So here you have this light blue color. That means that it's not yet ready. And I forget one. Action health checks. You can do this also using it has modified it. Okay, let's wait. Okay, now I can make it. You can do everything using YAML if you love YAML. Well, some people do, you know. I can show you how it looks like in YAML, by the way, because you can edit the YAML directly from here. That looks like that. That's fun, no? You need to add all this. Okay, so now normally I should have my two pods that are going to be ready. Come on. Running. That one is not yet ready. Both are ready. So something that we can also do here is going to the log, to the terminal of your pod. And in the terminal you do PS. Oh, process IDs. What a developer do with process ID. Oh, it's 6. Let's kill it. So we killed one of our microservice. And we see here, oh, it automatically detects that it's not ready anymore and restart it. And as soon as it detects that it's not ready, the traffic doesn't go to that one. And it's going to fix it and restart it. And if you go here, you see container restart 1. You don't have to take care about this. Kubernetes is doing that for you. That's kind of cool, except that you can't kill your system anymore. It's always restarting, which is a little bit annoying. Okay, I've done the first microservice. Let's do a second one. This second one is not going to be deployed using a Docker file. I'm going to use the Fabricate Maven plugin that works with OpenShift and Kubernetes, and that will just do exactly the same thing, but we don't have to write. So here is the code of my second microservice. We have health checks and so on, and I need to. So this second microservice is going to consume the first one and also the pricer service that is deployed here. And we'll try to guess how much money I need before going to do my errands by calling the pricer service and checking and telling me how much every product is going to cost me. So I need to use the service discovery to retrieve my two services. These ones are HTTP endpoints. So I just do that like that. And look, this is a data stream of one, a single data stream. Then I need to be notified when both are here. Okay. Pricer shopping. Okay. And then I will do shopping equals shopping, pricer equals pricer. Okay, and then just start my HTTP server. So when both has been resolved, I just do this. Yeah. And no, I need to subscribe, because if I don't subscribe, nothing is going to happen. And then I need to call my shopping service to retrieve my product list, and for each of them, I need to call my pricer service. So this is what calling my shopping service. I will go that map, flat map. I got a JSON object, so that's my shopping list. I will create a data stream for all entries of my JSON object, like this. Then for each entry, I'm going to call the pricer service. So as we are very limited in terms of time, I'm going to use retrieve pricer. So I pass the pricer and the entry. Okay, and now I can subscribe. Why am I not happy? Flat mat single. So now I'm going to call it for every product from my product list. So for every product I retrieve, I'm going to write in my HTTP response this. Response and the JSON object. If an error happens, I'm going to fail. And when I have retrieved everyone, I'm going to close my HTTP response. And let's deploy this. Okay, so a couple of things here. I'm using what we call chunk request. Because I don't want to write everything in my request in one big go, in one big blob, I will write it as soon as I have something, and when I'm done with everything, I am ending the request. That's actually very important in terms of memory, because if you have 10,000 users and you retrieve and keep everything in memory, then you have 10,000 times what you want to keep in memory. That doesn't scale. So to avoid this, use chunk request. And you know what? Chunk request exists since HTTP 1.1. So it works. This is pushing the Docker image. 26 layers? Man, they change things. So the first one had only 4 layers. This one has 26 layers because this one is a production image made by our production team. So they had things like monitoring, metrics, security, everything that is very boring, they had it for me. That's why there is 26 layers. And let's see. Hopefully it will be just in time. Come on. We can improve the code here. No, doesn't want to. Let's check if build is passing or not. Ooh, since 1 minute. 99%. Okay, push successful. So it should instantiate it. No. Please instantiate it now. Deployment, shipping backend. No, it doesn't create it yet. It's going to create it. It's just a little bit slow. When you run the cloud on your laptop, you can imagine that. Things tends to be a little bit slower. Okay, let's see. It's going to come up eventually. So that's, obviously, as soon as you switch, it starts doing things. Okay, so now it should start it. Shopping list service here. It already has the health checks configured because the Fabricate Maven plugin does that. And if I call it, it calls my shopping service, retrieves the 3 entries, and for the same, and then calls the pricer service for each of them. It calls them in parallel because if the shopping service, if the pricer service start to be slow, you don't want to call them concurrently, sequentially, but in parallel. That's all I have. I believe. How much time do I still have? It's over? That's all I have. If you wonder why Vertex, Vertex lets you be, as developer and architect, back in charge. We don't tell you how you are going to build your system. You do whatever you want. It's going to efficiently use your CPU and memory resources. So if you start thinking that you can put your monoliths in a containers, then you need a very big container host and tuning. So Vertex will let you build lightweight, reactive, asynchronous microservices, and microservice is just one of the things you can do with Vertex. If you want more information, you can ping me at my Twitter account, Clement Plop, or by mail. Vertex project is also on Twitter, and you have the address here. And at the bit.ly address, you have a book, a free ebook that you can download for free. It's a PDF. I wrote it, so it's a small one. It's 70 pages, and you will have way more information about Vertex and how you deploy it on the cloud, or you containerize it, and so on. Thank you.